Okay, so few people are joining. That's good. I share my screen. I hope my screen is visible to you all.
Visible, ma'am.
Okay, all right. So in today's class, we'll continue with the topic of biomaterials. So those who have missed yesterday's class, let me just quickly summarize on what we have done in the last class. Yesterday we discussed the article number 4, okay, and we look into what experiments did they do, what results did they obtain from it, and how like those results are significant to us as tissue engineers. And also we started with the new topic, biomaterials, all right. And we have looked into the classes of biomaterials. Like there are three classes that are used for tissue engineering applications or for fabrication of medical devices. These are metals, ceramics, and polymers. So under polymers, we can again classify into natural polymer or synthetic polymers. All right. And we have to like while choosing a biomaterial for making a tissue construct. So why biomaterial would you use? You would use it to create an artificial ECM on which your cells will gain support and grow. All right. So for making any artificial tissue, you need an artificial ECM, that is a biomaterial, but you have to first define some parameters on basis of which the choice of the biomaterial will be taken. Okay. And also we need to make sure that the biomaterial chosen should be biocompatible. Means your applications, for example, you want to create a hard tissue like a bone, okay, and you want to create you choose a biomaterial to be used for creating that bone tissue. So the properties of that biomaterial should be such that the property of the bone should be mimicked. So there are some properties of a material that we look into. First is the bulk properties. Okay, we have started with the discussion of what kind of bulk properties that people characterize. Okay, then we will look into the surface properties of the biomaterial, because ultimately it is the surface that the cell can sense. Okay, and then we will also see how our body reacts when we implant some foreign biomaterial into our body. So whatever artificial tissue that you will make using cells and material and whatever bioactive factors, when it is implemented on our body like in vivo system, our immune system will attack it. So how does that thing goes on? Okay, so we will also look into that. So in today's class, we'll continue with our discussion on characterizing the mechanical properties of a biomaterial. So yesterday we started this topic. So when we see what are bulk properties people study, first is the mechanical properties. Okay, so mechanical property, we have looked into the Hooke's law, which gives the linear stress strain relationship, and the modulus that the people measure, the Young's modulus and the shear modulus. Also we looked into how the modulus measured using a machine called mechanical testing device. Okay, so we will just continue on that topic only. So if you recall, we have discussed metals, right? Now, what primary bonds are there in a metal? So, because of that kind of structure, it has the property of plastic deformation. If you remember, we have discussed this. So, people have also seen that it is a ductile material, means you can stretch it to make wires, or it is also malleable, like you can create sheets out of it. So these kind of characteristics come from why it comes from the metallic bonds that are there between the atoms. So this is the line, this two lines actually is based on the graph that we discussed, that we ended with in yesterday's class. So if you remember, there was a region, toughness, that the area under the curve is the toughness, right? And the linear relationship between stress versus strain is the elastic modulus. The slope of that line will give you the elastic modulus. Also, some parameters we can define from that graph, where the ultimate tensile stress, it is the stress at which the material breaks. So from that graph also we can calculate the ductility. Okay, that is how much plastic strain that the material has undergone. Plastic strain or plastic deformation. So plastic deformation means how much of the change in the length has happened irreversibly. Means when you remove the external load, the material does not go back to its original length. Rather, some additional new length has been added. Okay, so that this phenomena is called plastic deformation. So that's why metals are highly ductile, because they can undergo very long plastic deformation until they fracture, means they breaks. Okay, uh, this kind of characteristic is not seen in ceramics. Okay, so some these little material properties we should know before choosing your material for the particular application. Okay, so if you remember, we have discussed one class of the material, that is called polymer. So under polymer, there is a small class of biomaterial that is called hydrogel. Like under polymer only it comes. So hydrogels are those kind of polymers which has the ability to absorb a large amount of water and swell. Okay, so when you use hydrogels, we actually try to mimic the aqueous environment in our body. So this statement basically says that when you are testing the mechanical property of a hydrogen, then what you should do, you should first immerse your hydrogen sample in water bath, so that it absorbs a large amount of water, and in that swollen state you measure how much strength does it have. Okay, so this is a special case of how a particular material, for a particular material you will do the characterization for testing, mechanical characterization you will do. Then people also do biaxial testing. Means in previous class we said that we apply load in only one direction, say in x direction or in y direction. But for those materials which are anisotropic in nature, so anisotropic materials are those materials which like at every point within the material you will get some different value of a property. Okay, that is called anisotropic. A reverse of that is isotropic materials. Okay, so human tissue, all human tissue are anisotropic in nature. Means at, if this is the material and these are the points within the material, and you measure what is the value of say Young's modulus at this point, so you will get one E1 value. Whereas in this point, if you measure in a different direction, you will get some E2 value. The Young's modulus will differ. So for these kind of material, depending on in what direction you are measuring, the value of the property changes. That is called anisotropic. So that is why people do biaxial, means they apply load in say in this direction as well as in this direction. So in multiple direction they try to apply load, either compressive load or tensile stretching load, for characterizing these anisotropic materials. Now, so when we look into the small class of, it's a very big class of material, that is polymers. The polymers are, many of the polymers are often characterized as viscoelastic. Means they are having elastic property as well as viscosity. So if you recall, viscosity is a property that is usually seen in fluids, liquids or gases, right? So viscosity, if you remember, the this symbol we use, right? It shows how much fluid is given resistance to a shear, right? uh, and if the resist if the if so for a high low viscous liquid like water, you know, it can easily flow. If you apply like pressure, like in form of shear, then it will easily flow. Whereas for highly viscous material like honey, for example, it will flow very slowly. So that is why so this viscosity property is usually defined for the fluids, whereas the elasticity is usually defined for solids. But there are some materials which display both the viscous nature and the elastic nature. Those are called viscoelastic materials. And the polymers are most of the polymers are viscoelastic in nature. So that is why we use the theory of viscoelasticity to characterize various kind of polymers. So the viscoelasticity comes from how the structure of the polymer chain is there, means how the polymer chains are oriented, and is there any side chains and not. Okay, so because of the structure of the polymer, the viscoelasticity comes in play. And for characterizing this viscoelastic behavior of this polymer material, we cannot use the mechanical testing device that we previously talked about. Okay, for measuring the modulus, we use separate kind of a technique. And there is actually a big field that studies the flow of this viscoelastic materials, how they are flowing. That field is called rheology. Okay, so I will not go into deep, just it's a primer for you guys, so that you know some part of it and maybe apply in future. So they use a machine called dynamic mechanical testing machine for characterizing the viscoelastic behavior, where samples are prepared as thin samples, thin strips. Okay, and on one side shear is applied continuously, and this shear is varying with time. And then they measure how much change in length has happened due to this shear. And this type of testing, as I said, it comes under a very big field of rheology. Now note that whatever testing that we are doing, either we are measuring the viscoelastic behavior or we are measuring the elastic behavior for a material, the values that we will get, it will help us to understand whether or not our biomaterial has the property similar to that of implantation site. So if you are trying to make a bone substitute and you're going to fix it with a broken bone, you need to make sure the mechanical properties, means both the elastic behavior and viscoelastic behavior, those are similar to a native bone. Because that, if that is not there, then your artificial tissue will fail. And if it fails, you can imagine how uh, dreadful that be for the patient. So we always need to make sure that the properties of our biomaterial should match with the surrounding tissue. And many of the biological tissues, they are, when people have tested their mechanical property, like say for example a bone or a skin or a liver, so their testing often uh, tells people that it is highly non-linear, means you cannot correlate easily using few parameters, like x is dependent on y. Okay, it is not a linear relationship, you cannot use a simple expression, but it is non-linear. You have to bring in the partial derivatives and all in order to explain the mechanical properties. So as I said, matching the mechanical property of a biomaterial to the surrounding tissue is important, but it is also quite challenging, because the mechanical properties of these tissues, they vary a lot. Okay, they vary a lot. So this particular table, you can see that these are different types of tissues that are taken from the body. All right, and say collagen fiber, elastin, you know, these are the natural ECM present in our tissues. And if you compare the elastic modulus of this ECM component only, and this is the tissue, cartilage and skin, where the collagen and elastin is found, you can see there is a change in values of elastic modulus. In tendon also collagen and elastin is found. Muscle also some amount of collagen is found. So even though that component is present in our tissue, the mechanical property of the tissue and the mechanical property of the material, they are highly different. They're very much different. The same things goes with the yield stress. That yield stress means how much stress is required and for causing plastic deformation, means shifting from the elastic region to the plastic deformation region. That point is gives the yield stress. And then the maximum strain means maximum strain that the tissue or the material or the maximum deformation that the material tissue can undergo before it breaks. So these values, they are highly different, and you will see that is why that in some paper uh, the elastic modulus of one tissue is different from the another paper. So the values also people are reporting in different way, because it is quite challenging to say that there is a unique value of the elastic modulus for a particular type of tissue. And also tissue characteristics, they change with the age of a person. Okay, so if you do mechanical property characterization of a tissue taken from a young child and compare it with the person taken like who is old, then the values will dramatically differ. And apart from mechanical properties, just I discussed, we also measure the thermal and the electrical properties of the biomaterials. So thermal properties, like in thermal property, we basically see what is the TG, glass transition temperature, the melting temperatures of a material. And what kind of material we generally see? We generally see it for polymers. For polymers, when you're working with polymers, understanding of thermal property becomes important, because there are various types of polymers. uh, they have a very low very low melting point, and if it is say lower than your body temperature, then the polymer structure won't be maintained. So you have to choose accordingly what is the melting point. And then there is also another thing called glass transition temperature. So it is, this temperature is seen for those kind of polymers which do not have a crystalline structure, they have a amorphous structure. So like they transition into a rubbery kind of a state. Okay, a gooey rubbery kind of a state. So that is another thing that people study for a particular type of a polymer. So graph this graph actually shows you um, that this is for the amorphous material, means it does not have a crystalline structure. The atoms are not ordered, arranged in a highly ordered manner. This is for the amorphous material. So for the amorphous material, studying of the glass transition temperature is important, because below this glass transition temperature, the material is glassy, means the polymers are almost orderly arranged, means in amorphous you cannot create a highly ordered structure, but the polymer are in place, they won't change their positions. Okay, they're almost arranged, not perfectly, imperfectly arranged. This is the glass state. But when the temperature is above the glass transition temperature, then the material becomes a rubbery kind of a structure, where there is some flow. The material starts flowing. If you give us even a small amount of shear, the material will start flow. Whereas for crystalline material or semi-crystalline material, you have something called the melting temperature. So below this melting temperature, the material is perfectly solid, means retains or has a crystalline structure. And when the temperature is higher than melting temperature, then it becomes a liquid. So that is the meaning of the melting temperature and the glass transition temperature. Again, I'm repeating, the studies of this temperature is important when you're working with polymers, okay? And you are going to use this polymer uh, at locations in the body where the temperature is high, okay? And you have to understand whether at those temperatures what kind of crystalline state it becomes, okay? So yeah, then also for various polymers or various type of materials, people study their electrical properties. So when you are choosing your material for tissues like cardiac muscle or neurons, where in these type of tissues there is a transport of small electrical impulses, and you want to make sure that your material can like match those properties, then you have to also test their electrical properties. So what electrical properties people measure? They measure their conductivity. With conductivity is ability to uh, transport electrons, means transport electric current. Then piezoelectric and star storage capacities, these things people measure, okay? So it is quite similar to the electrical properties people measure for a battery, okay, or for a material that is going to be used for a battery or a super semiconductor, supercapacitor, etc. But for these kind of tissues like neurons or for heart muscles where the electrical impulses are getting transported, you have to also consider characterizing their electrical properties. All right. So is there any query so far? Because now we will shift to another class of properties that people measure for a biomaterial, that is the surface properties. So is there any query? If I'm going too fast, you guys can let me know so that I can slow down. But is there any, if there is any queries, you can also interrupt me in between and ask for explanation.
No queries now.
All right. Thanks. So now we will start with another class of properties that people look into for a biomaterial, that is surface property. The surface, you can understand the interface on the solid, okay? Solid air interface, that is the surface. So the interaction between a material and a cell, they are dictated by what kind of interaction, surface interactions is possible. Means if, so this is the material. So far we have discussed the bulk property, this is the bulk, and this is the surface. Cells will always interact with surface because it will always see what is on the surface. So it will interact with the surface through various kind of bonds. So there are non-specific bonds, then there are specific ones, and as well as the surface topology. It will also affect how the cell is interacting. Surface topology means whether the surface is rough or smooth, etc. That is the surface topology. Now, what kind of non-specific interactions comes into picture between cell and a surface? So there are van der Waals forces, then electrostatic forces, charge interaction, positive, negative charges. Then there are solvation forces, steric forces. Sorry, solvation forces like correspond to uh, the water, like how the water molecules are adhered on the surface. It can adhere, right? Or what kind of bond groups are there. If there are bulky groups on the surface, then it will also interfere with the adhesion of the cell on the surface. Then specific binding interactions are also there, means uh, it is mediated through basically the cell surface receptors and receptor ligand interaction I'm talking about. These are highly specific. So what are receptors? I know you guys already know about it, but receptors are basically present on the cell surface, and they are transmembrane proteins with uh, glucose or the carbohydrate moieties attached to them. Okay, and they are like at the length scale of 2 to 50 nanometers. They are very small. So often people have observed, like it is not often, it is always the case, specific interaction, specific receptor ligand interaction, it always dominates the non-specific interactions, whether the non-specific interaction is attractive one or repulsive one. And it happens on a length scale of nanometers. As you can see, receptor is only 2 to 50 nanometers. So specific interactions dominate the non-specific interactions. And there are various classes of receptors available on the cell surface. Like we have already seen, there are selectins, cadherins, then integrins, then proteoglycans, immunoglobulins. So these all receptors are there, and if it finds suitable ligands on the surface, then specific interaction will take place, and because of which the cell can adhere on the surface. Now, this now from this topic onward, it is bit complicated. Okay, so I will like go slowly. I will try to go slowly, but if you guys face any confusion, let me know, because this topic that I'm going to explain, how cells adhere, the big question is that how the cells adhere on the surface and what goes on the surface. So this is bit complicated to understand. So if again I'm repeating any queries, let me know. So people have used various thermodynamic models, or taken few thermodynamic models, modified it, and applied in this scenario to explain how the cells are being adhered on a surface. So one such thermodynamic model considers, or it basically shows or compares the liquid droplets. Okay, it compares liquid droplets to cells. Okay, and compares that the liquid droplets, when they interact with the surface, it is homologous to cell interaction on the surface. Okay, and this interaction takes place in a fluid. So the surrounding medium is a liquid or air. So this is the model. This is the surface, this is the liquid droplet, and the surrounding environment is a fluid. And this model is modified in this scenario, where the liquid droplet is what do you say, like considered that it can be replaced with cells, and it is modified accordingly. So there is a person, Young. So he has proposed this equation, Young's equation, to help us understand how cell and the material surface interact. So in this equation, this gamma, these are the surface tension. So I think you guys have studied what is surface tension in your class 12th standard. So these are the surface tensions, and surface tension is measured or takes place between two interfaces, either liquid solid, or liquid vapor, or vapor solid. So these three states of matter, all three states of matter exist in this particular system. This is the solid, this is the cell is compared with the liquid droplet. So this is the liquid. Okay, and surrounding is some vapor, say. Okay, some gas medium is there. So all these three states exist in our system. So this equation can be used. And theta, okay, cos theta is a new quantity which is called contact angle. Okay, so this Young's equation describes a system of a drop of a liquid sitting on a surface with the solid vapor, solid liquid, and vapor liquid interfaces in equilibrium. So in equilibrium condition, or at rest, as I said, when there is no driving force, at that condition this equation is defined. And this equation helps us to measure the contact angle. Contact angle is the angle, so this is the liquid droplet is sitting on a material. So what is the angle it has made? Okay, what is the angle it has made with the surface? That is the contact angle. And the Young's equation can be modified and used to explain how the cell or how the cell is interacting with the surface by this expression, where F adhesion is the interfacial energy of a cell with a solid biomaterial in a liquid suspension. Okay, so cell uh, so the if you see in the previous equation, there was no cell here. Okay, we didn't use C as a subscript anywhere. There is L, V, S. Okay, but now we have modified that previous equation to incorporate cell interaction, cell solid surface interaction, cell liquid interaction, and solid liquid interaction. These three states are there now for this particular equation. And when we know the surface tension with respect to all these interfaces, we can get what is the interfacial energy, means how much energy is being used for adhesion of the cell on the surface of the biomaterial in presence of a liquid environment. Now note, so I don't know how much you are understanding, but if there is any doubt, you guys let me know. For hydrophobic surfaces means water repelling surfaces. They don't like water. For hydrophobic surfaces, the contact angle that the water droplet makes on the surface is greater than 90 degree. So that is why you will see water droplet forming beads on hydrophobic surfaces. Also, on these surfaces, the surface tension for solid liquid is a very small value. Okay, and the force free that is free energy, actually, right, free energy of adhesion for a cell is positive. So when these three conditions are there, uh, it makes the hydrophobic surfaces highly unfavorable for cell adhesion, means cells do not adhere properly on highly hydrophobic surfaces. So that is one point to note. So if a biomaterial has groups on the surface, that makes it highly hydrophobic. So what all groups you can imagine? So there will be carbons, okay, and means hydrocarbons, basically CH groups are more there, and aromatic groups, okay, with no means oxygen or no nitrogen groups. So these all groups make the surface highly hydrophobic. Okay, and on hydrophobic surfaces, the contact angle is quite high, the free energy of adhesion is positive. Okay, and the surface tension is also a small value, so because of which the cell does not adhere favorably, cells do not adhere well. Whereas in hydrophilic surfaces, means those surfaces which loves water. So if you give a drop of water on a hydrophilic surface, the water will spread. Water drop will spread. It will not form a bead. So on those kind of surfaces, the contact angle that the droplet forms with the surface is less than 90 degree. The surface tension is very has a large value, and the free energy for adhesion is negative. Means under these conditions, the hydrophilic surfaces, they are favorable for cell adhesion. All right, so now you can understand that if we can know what is the uh, hydrophilicity or hydrophobicity of a biomaterial surface, then it will easily correlate with whether it is favorable for cell adhesion or not. Means whether you can use it for making a tissue. So what does the logic say? Our logic dictates that while choosing a biomaterial, we will choose that biomaterial which has a hydrophilic surface, so that cells will adhere to it, because we are working with adherent cell type. So, and if the cells do not adhere, then the subsequent cellular fate processes will not happen and will not see the resultant function. Now, although this equation that it is we just saw, this equation is good enough, means sorry, yeah, it's good, means it can be used to accurately describe cell adhesion on various surfaces. On various surfaces you can use this particular equation, but it has some exceptions, means this equation fails to explain this phenomena under some conditions. First is when receptors and ligands comes into picture. So let's read it, what is written here. Imagine that the presence of a specific receptor ligand on the surface may dramatically alter specific interactions with the surface. Correct? So in that case, the value of this particular quantity, gamma Cs, it will change because the cell and the surface, solid surface interaction is being affected by the presence of a particular ligand, okay, on the cell surface. And the presence of this so the ligand is there, so some receptor will be there on the surface. The presence of this receptor, however, won't have any effect on the solid liquid interface surface tension. And it is when we are trying to calculate this quantity gamma Cs, then we need this quantity. All right. And since there is a contradiction in our model is doesn't accommodate the correct values of these two values, gamma SL and gamma CS. So the values that we predict for the free energy is incorrect in that way. So because of that, we do not get the correct picture of how the cell addition is happening on the surface. Is this point clear? So due to presence of specific interaction, this ligand receptor interaction, the values that we will measure for gamma SL, that is surface tension between solid and liquid, and surface tension between CS, that is cell and solid. So those values are not predicted accurately. Because of that, the value that we get for the free energy is not correct. So this whole model then fails to adequately explain the behavior of cell adhesion to the surface. Okay. And there is one more exception. This model does not take into account is that when, as I said in the previous slides, hydrophilic surfaces are good or they favor cell adhesion, whereas hydrophobic surfaces, they do not favor cell adhesion. But if the surface becomes very hydrophilic, then also cell adhesion won't happen, and this condition is not taken into account by the model. Okay. So another exception that this model, this expression that we just saw, doesn't take into account is the effect of protein adsorption on the surface. Okay, so that is another very important topic that we should know. So usually what happens is, this is your biomaterial surface. Some water molecule first interact with it, okay, and then some proteins will come and interact, and on top of it the cells will adhere. So this is how the molecular picture is. So where, and this protein is coming from say blood. Blood has serum and all, and there are various kind of proteins in the serum. So from the blood your protein will adhere on the surface. or adsorb on the surface. So ultimately, it is the protein layer which the cell sees on the surface, not the surface itself. Correct? So the process of protein adsorption, it dominates on how the material is going to behave for a particular physiological application. Okay, the layer, what kind of proteins are getting adsorbed on the biomaterial surface will dictate what the cell sees first, and then it will dictate whether that material or whether that device is going to be rejected by the body, or like how the host will react and in the presence of that foreign uh, material. Okay, so is there any query? So let me again repeat from the previous discussion that what we understood. We 2 points to keep in mind. First, the hydrophobic surfaces, they do not favor cell adhesion. Okay, because the contact angle is very high. Um, the force, free energy, F adhesion, the free energy uh, for the cell interaction, cell surface interaction is positive. So hydrophobic surfaces, they do not favor cell adhesion, whereas hydrophilic surfaces, they favor cell adhesion. But if the surface is highly hydrophobic, then also cell adhesion won't happen. So these 3 points you need to keep in mind, because now we will see how the protein adsorption is going to change these 3 points. All right. The protein adsorption, or the protein can adsorb either through electrostatic interaction or hydrophobic interactions, or through hydrogen bonding, or all three can play, like all three can contribute for adsorption of the protein on the solid surface, solid biomaterial surface. The surface properties of the biomaterial, it can affect what is the rate of protein adsorption, how much of the protein is adsorbed on the surface, and what is the mechanism followed. So this part basically hints on whether the biomaterial is hydrophilic or hydrophobic. So what I'm trying to say is, hydrophobic surface will adsorb protein differently, whereas hydrophilic surfaces will adsorb protein differently, and indirectly it will then affect how the cells will adhere on the surface. Okay, so a general rule is, if the surface is highly hydrophobic, then protein adsorption will happen a lot. It means large amount of protein will adsorb on the surface, or you can imagine majority of the surface will be covered by the protein if the surface is hydrophobic. Now people have also observed that during and after adsorption, the protein can undergo some transformations, like it can undergo conformational transformations, uh, and that in turn affect how the cell will adhere on the surface. So there are three mechanisms by which surface properties modify the cell response through protein adsorption. Or you can say, uh, so these are the three mechanisms that shows how the protein is adsorbing on the surface, and that in turn is affecting the cell adhesion. So first mechanism is applicable when there is multiple proteins available in a solution, like say your serum has large amount of proteins, and when it comes in contact with your material surface, then how each of these individual proteins are getting adsorbed on the surface, that in turn will affect how the subsequent cells will adhere. So one example I have given in this particular diagram. So let's say there is a protein labeled as A, and it is a I think mixed with various amounts of. Okay, so A is fibronectin, sorry, fibrinogen. A is fibrinogen. Okay, A is a protein, fibrinogen, and B is another protein, it is albumin. So in this experiment, they have labeled the fibrinogen, radio labeled it, whereas albumin is not labeled, and a mixture is created of albumin and fibrinogen, and the relative proportion of these two proteins, they are varied, and they what they observed is the tendency of fibrinogen to adsorb on a particular surface, it always declines when large amount of albumin is present. So albumin, large amount of albumin is hindering the amount, how much amount of fibrinogen can adsorb on a surface. So this, there is a basically a competitiveness on between the fibrinogen and albumin. So they are competing for space to and then subsequently adsorb on the surface. So this is the curve. So for say one surface type 1, the maximum amount of fibrinogen that can adhere is different. Okay, this is, then you will see in surface 2 also the peak of amount of fibrinogen that can adhere is different. So depending on what type of surface you are using, the amount of fibrinogen, the maximum amount of fibrinogen that can adsorb in presence of the competitive protein, that is albumin, is varying. But similar kind of competitive graphs you will see even if the surface is same, because the mechanism by which the fibrinogen is adhering and the albumin is going to adhere is different. They are not following the same mechanism for adhering on the surface, because then that also brings in different curves. Okay, then another mechanism, the first mechanism is competitive adsorption, uh, and that is applicable when a mixture of protein is there, and you will see one protein has a tendency to adsorb much more strongly on a surface than the other protein, or one protein is hindering the adsorption of one protein. Okay, now due to surface properties, some protein can undergo conformational changes, and that can in turn affect how the cells is going to respond to that surface. And the third point being, if we immobilize a protein permanently on a surface, then what is going to happen, and the concentration at that particular region is going to increase, that in turn going to what do you say, increase the time scale for which cell and material interaction is going to happen. Signaling is more sites at the protein will become available to which the cells can bind. Okay, and prolonged signaling can also be seen. So these are the three mechanisms through which protein adsorption is affecting cell adhesion on a particular biomaterial surface. So I really don't know how much you have understood so far. Okay, because it might be a bit confusing. But if you haven't understood anything, okay, and you want to ask me like, what did you teach so far? So this is the perfect figure for that. So on the surface, first, depending on what kind of surface it is, whether it is hydrophilic or hydrophobic, your water molecules that is there in the aqueous environment, they will adsorb. So it can either adsorb using bonds like hydrophobic bonds or van der Waals bonds, or it can adsorb using hydrogen bonding or electrostatic charges. So you can imagine, if the surface is hydrophobic, then the interactions like hydrophobic interaction, van der Waals interactions will be favored between the surface and the water molecule. And if the surface is hydrophilic, then hydrogen bonding and then ionic interactions, these kind of interactions will be favored. So depending on the surface type, your water molecule will adsorb, and how they are adsorbing, what kind of bonds are involved, those will dictate the orientation and the strengths of those bonds. Okay, so it can form a cage kind of a thing, or it can strongly adhere to the surface. So first, surface and water molecule interaction takes place. Next comes in the protein mixtures that is present in the blood, say. Okay, the protein then sees the surface, not directly, it sees the layer of water molecule that is adsorbed. So depending on how the water molecules are adsorbed, the adsorption of protein will happen. Okay, it will affect the way the protein, or the mechanism by which the protein will adsorb on the surface. It can either adsorb in such a way that the native structure of the protein remains intact, or it can adsorb in such a way that the protein structure becomes denatured. Okay, so and so these are the two mechanisms, the two ways in which the protein can adsorb on a layer of water molecules. Then comes the cell. So cells will see the protein layer. Remember, it will not see the biomaterial. So if the protein is adsorbed in its native condition, where necessary cell binding sites are exposed properly, then you will see the cell will adhere nicely. Okay, whereas in the second case, if the protein has denatured, so various cell binding sites are masked, cell cannot see them, then the cell adhesion will not happen properly. So in this way, the cell ultimately adheres on the surface. Now the statements that we said in the previous slides, like how the hydrophilic surface affect cell adhesion, or how hydrophilic or hydrophobic surfaces affect protein adsorption, we will now put those statements into this figure. Now suppose if this surface is hydrophobic and this surface is hydrophilic, then hydrophilic surface will have some, say, positively charged groups. Okay, and due to that, the water molecule is very strongly attracted towards it, and this type of attraction is so strong that uh, it forms, what do you say, difficult to break bonds. Okay, you cannot, or the water molecules is not ready to leave the surface, so that can happen. And in another case, if there is hydrophobic surface, then the water molecule is like loosely attached, right, through hydrophobic interactions, so they have a more tendency to leave the surface. All right, so in those cases, what happens, when the protein comes and adheres on a hydrophobic surface, then this water molecule is ready to leave. All right, if it leaves, the entropy, total entropy of the system increases. All right, and that in turn favors the adsorption of the protein. So I'm basically bringing in the principles of thermodynamics. If you remember second law of thermodynamics, the the universe is always trying to increase its entropy. And that is why some process becomes spontaneous. So here also same thing is happening. The release of water molecule, easy release of water molecule from the hydrophobic surface is increasing the overall entropy of the system, and that is highly favoring the adsorption of protein. So that is why this statement that we saw, no, highly hydrophobic surfaces lead to greater protein adsorption, this statement is now we have used it. Okay, so now But in this hydrophilic surface, if yellow one is hydrophilic surface, here the water molecules have a lesser tendency to leave. So the net gain in entropy is lesser. So the extent to which the proteins can adsorb becomes less. Okay, and it is often seen if the protein is not adsorbed, then the cells won't adsorb. So highly hydrophilic surfaces, if you remember that statement, they do not favor cell adsorption. Okay, sorry, cell adhesion. Whereas hydrophobic surfaces, they like favor cell adhesion. But in literature, when people have studied the effect, like how much hydrophobicity do you need to uh, promote cell adhesion, and what is the limit of the level of hydrophobicity that the cells won't adhere. Okay, so when they have studied or tried to answer this question, they have come to a conclusion that we need optimum level of hydrophobicity and hydrophilicity for optimum cell adhesion. So there are few materials which are highly hydrophobic, that is they are towards one end of the line. Okay, they are highly hydrophobic. That also doesn't favor cell adhesion, because if the surface is highly hydrophobic, then uh, the the interaction between the protein and the surface can cause degradation of the protein, and if the degradation of the protein happens, then the cell won't adhere properly. And on the other end, if the surface is highly hydrophilic, then the protein won't be able to adhere. Okay, it won't be able to adhere because the net gain in the entropy of the system is very less. The system is not favoring protein adsorption on highly hydrophobic surfaces, then also cell will won't adhere. So we have to come in middle, we have to find a middle ground where the hydrophobicity level and the hydrophilicity level is optimum, so that the cells can adhere properly. All right, so I hope I gave you a proper conclusion to this topic, and if there is any queries, you guys let me know. Any queries?
Ma'am, what is
Yeah.
solvation force? Solvation and steric force.
Okay. So solvation forces basically, um, if you so what we have discussed, the interaction of the water molecules. So water molecule usually is the solvent. Water is present in a large amount, and within water there are some ions present. So those are the solutes. So how the solvent molecules and the solute molecules, they're interacting, what kind of forces are there. Okay, so those refer to the solvation forces or solvation effects in general. All right, whereas steric effects basically corresponds to how the structure of a chemical molecule is affecting the interaction between certain groups. So if I say in this particular example, if your surface, usually it doesn't happen, but if your surface has large aromatic groups like benzene groups or phenylalanine, large aromatic groups, where like at the molecular level, your water molecule is not able to interact. Okay, is not able to see the surface, means because of the presence of large molecules, the polar groups are getting masked. Okay, so that is the steric effect that people say. Okay, that is what you will find explanation from a chemist as well, means one large group is interfering the interaction between say two like groups, say one polar and two polar groups. So these effects also are non-specific. They do not, and also the effects that they have on the bond, the strengths. So those are very less. They're weak. They form weak bonds, or their contribution is quite weak. If some specific interaction comes into place, they will definitely dominate these effects, the solvation effects and steric effects. All right. Any other queries?
Is it like if there are two equal forces, how a different force comes and intervenes? Is it like that?
Uh, can you repeat?
Is it like there is a A and B molecule which has same properties?
Hmm?
Another molecule C like comes and intervenes with a different property. Is it
Hmm?
like that?
No, no.
Is that what you meant? No? Okay.
So, so steric, the word steric refers to conformation. Okay, how the molecule, the atoms in the molecules are present in a 3D space, their conformation. Okay, so you must have heard this term when you were studying about resonance and the hybridization, these things in your class 12th when you're studying chemistry. Okay, so there are various conformation of a particular group. So if there is a very, very large molecule with different types of groups, like some benzene groups, some oxygen atoms, some nitrogen atom. Now, it can happen that this large molecule, say a polymer. So, if example is say polymer. Polymer is a very, very large, what do you say? Very, very large molecules, right? And various kind of atoms are present in a polymer chain. Now, in presence of a large aromatic group, usually steric effect comes from the aromatic groups only, large aromatic groups like benzene and all. They uh, they can interfere with how, say, oxygen or interacts with the hydrogen. Means it can interfere with the extent of hydrogen bonding. Okay, so this, when this kind of thing goes on, it is, we say, steric interference is happening. Okay, so maybe you can look into a bit into like from a chemistry point of view, because these things that I'm trying to explain is given by the chemist, and they have defined it for particular type of atom or functional groups. It is valid only for particular type of functional groups. All right, we cannot generalize it for a molecule A is interfering with molecule B. It is not like that. Okay, so steric effects usually comes when we're talking about bulky and large groups, large functional groups. Then people say steric effect is like come into the picture. You get my point?
Yeah, got it, ma'am.
All right. Okay. Any other queries? So I hope you have understood how the cell adheres on the surface, how the hydrophobicity and hydrophilicity affects that, and the protein adsorption is basically completely changing the cell and material interaction when the proteins are involved. Okay, so I hope you have understood that point, because it is very, very important for us, because ultimately whatever material that you're going to use for, say, making a tissue or making a device, and that you're going to implant inside our body, it will definitely see the blood, and the blood has a large amount of proteins. Then you have to understand how the cells, surrounding cells in your host tissue, is going to then interact, is going to see your material, and ultimately whether that is going to cause rejection of your biomaterial, or it's going to be like function, it's going to function well in your body. So these things we will study a lot when we are going to discuss about the host material interaction, and we'll also touch upon the foreign body reaction. Okay, so that's it for today's class. Then I will quickly take your attendance and I'll share the notes with you. today only. And I'll also inform about like shortly I'll inform maybe tomorrow about what all classes, how many classes are going to be taken the next week. So because as I already told you guys in the previous week, last class, like yesterday, that we have a lot to cover, and we have very small time left to finish this course. My aim was to finish it by the end of this month, so I'll try to stick to that deadline. And like I'll keep the classes in the weekdays in the evening time only, after 7. So I hope that won't be a problem for you guys to join. Okay, but it may happen that we may have classes apart from Friday and Saturday, like on other days of the week also we can have some classes in the coming 2 weeks. Okay, so please try to join as much as possible. So let me take your attendance. So who all are present, kindly respond with their names.
Mutely, ma'am.
Okay. Okay, next.
Kirtan.
Kirtan. Vani, are you there? Nidhi, are you present?
Yes, ma'am.
All right. Janvi, are you there in the meeting? So Vani, are you there? Arshita?
Yes, ma'am. Nizama is there because she's pregnant.
Uh, sorry, Janvi, I could not understand what you just said. Can you repeat?
And Nizama is there in the
Okay, acha, acha, okay, there. Maybe she is facing some issues with her mic. Right. So Harshita is also there, no?
Yes, ma'am.
All right. Okay. So thank you all for joining. I'll share the notes and recording as usual, and we'll see you. Like I'll